The speaker is Camilla Pezzotti from the University of Vienna. Introductions. I leave the floor to Maria Pia for the introduction of the speaker. You have 45 minutes. Questions. Everybody has questions from remote, please write in the chat or raise your hand at the end of the seminar.
Thank you very much for coming. Good morning, everybody. It's my pleasure to introduce you to Camilla Pezzotti. I met Camilla just last January during the winter school, PhD winter school in Switzerland, and we found, I just discovered that she graduated and got her master's degree here in Rome at La Sapienza, and working with Marco Limongi and partially also with Alessandro Pieppi on stellar evolution modeling. And then she moved to Geneva to do PhD, working with Patrick Hegenberg and George Matisse, Menet, sorry. Working again on the stellar Geneva stellar evolution code, and particularly trying to evolve the star with the planet. And actually, after a postdoc in Geneva, now she is in Liège, and she is developing some other prospects. We are trying to find some similarity and working together, putting asteroseismology and the theory of star-planet interaction together, applying some evolution code that she refined and tuned during the PhD. So I hope that you will enjoy. Thank you very much, Camilla, for coming.
Hello, everybody, and good morning. Can the people online hear me well? I hope so. Many thanks to Maria Pia Di Mauro for inviting me here, and many thanks to the organizer of the IAPS Institute. And today, as Maria Pia said, I would like to talk to you about star-planet interactions with a particular focus on the impact of the stellar rotation and structural evolution on these studies and the key synergies with asteroseismology. Now, why should we care so much about star-planet interaction? Oh no, yes. So the need to understand these phenomena firstly stems from our daily experience. Indeed, we can every day experience the interaction that occur between the sun and our own planet, the Earth, for example, through gravitation, through the solar radiation, that helps to define the structure of our atmosphere, through the solar wind, but also through more energetic and abrupt events, such as the coronal mass ejections and the solar flares. In the past 2 decades, star-planet interaction studies have been further boosted and motivated by the continuous discovery of very diverse exoplanets and very diverse exoplanetary systems and populations. The diversity of these discoveries resides not only in the properties of the host stars of the system, some of which are shown here, which can be very much evolved, such as white dwarf, but also on the main sequence and very compact. This is the case for TRAPPIST-1. A diversity also in the multiplicity of host stars. This is the case of the Kepler-444 system, but also diversity in the system architectures. For example, exoplanetary system much more compact than what we are used to in our solar system have been discovered. Again, this is the case for TRAPPIST-1. And there are diversity also in the intrinsic properties of exoplanets themselves. For example, super Earth and mini Neptunes were not observed before these discoveries. Star-planet interactions are extremely useful and important whenever we want to understand how exoplanetary systems form and evolved. For example, they are crucial whenever we want to interpret some features of exoplanetary population. This is the case for the hot Neptune desert, that this region here in the planetary radius versus orbital period plane, that is particularly devoid of planets, not because of an observational bias, but because it is shaped on its lower edge by strong mass loss from the planetary atmospheres, and on its upper edge by high eccentricity orbital migration that brings planet very close to its hot star. And in this respect, star-planet interaction adds a time dimension to interpret these features that otherwise would just give us a snapshot of exoplanetary populations. Now, there are different types of star-planet interaction. There is the magnetic, the tidal, the solar wind, or the radiative ones. And all these interactions can have different effects on star-planet system components, such as the formation of chromospheric spots. In the case of the tidal interaction, it can lead to the orbital migration of the planet and the consequent spin up or spin down of the host stars. But also we can witness the formation of bow shocks around planets, the formation of planetary aurorae, and also the atmospheric evaporation. All these star-planet interactions do not act separately, but they are strongly interconnected, and they all depend on the host star structural and rotational properties, and of course also on the properties of the planets. And because of that, I'm sorry, I don't know. Because of that, whenever we want to study star-planet interaction, it's important to account as much as possible for the evolution of the host stars and the one of the planet at the same time. In my work, I specifically focus on these two interactions, which are the tidal and the radiative one, which I will explain a bit better in the following. Now, starting from the tidal interaction, so we know that stars and planets are generally submitted to mutual gravitational attraction. Whenever planets orbit very closely to their host stars, let's say within 0.1 astronomical units, we cannot use anymore the point mass approximation for the two objects. Especially for the star, indeed, we need to account for the differential gravitational force that is applied at the stellar surface and at the stellar center. And this differential gravitational force is the definition of tidal force. Because of this tidal force, there is a perturbation on the distribution of the mass of the star, so on its gravitational potential. And because of this perturbation, the mass redistributes approximately in the direction of the perturber, as it is shown maybe here in this plot. In an ideally frictionless case, the position of this redistribution of the mass would be perfectly aligned with the perturber. But since we know that in stars there are viscous processes at work, there is actually a misalignment between the tidal bulge of the star and the one of the planet. It either lags or anticipates the position of the planet. And because of this misalignment, a torque is applied to the stellar surface and the orbit of the planet that induces orbital migration and the spin up or spin down of the host star. Now, the tidal response of the star to this perturbed gravitational potential has two components. One is the equilibrium tide that represents the large-scale, non-wave-like, and quasi-hydrostatic readjustment of the star. And the second component is the dynamical tide that instead is the wave-like response to this perturbation. The dynamical tide can, in general, exist in all the region of stars that support waves, but in my work, I specifically focus on tides dissipated in all stars' convective envelopes. And in this specific region, they are excited in the form of inertial waves restored by the Coriolis force and are dissipated through turbulent convection. Now, depending on the evolutionary stage of the host star, one or the other component dominates on the migration of the planet. In particular, during the pre-main sequence and main sequence phase, when the star rotates faster, the dynamical time component dominates because it's strongly dependent on the surface rotation of the star, while the equilibrium time takes over at more evolved evolutionary stages. Now, I would like to just show you some equation to to indicate how strong is the connection between this phenomena and the stellar evolution. Now, we can consider the equation used in simulation to compute the variation of the orbital distance of the planet with respect to time for the equilibrium type. As you can see, A dot represents the variation of the orbit, and these other factors, such as tau CZ, which is the convective turnover time, mm is the mass contained in the stellar convective envelope, then we have the total mass of the star, the total radius, and also the surface rotation rate of the stars, all strongly depends on the evolutionary stage that we are considering. In particular, this last factor here, omega star over omega planet, where omega planet is the orbital frequency of the orbit, determines whether the planet migrates inward or outwards compared to the position of the star. A similar equation is used for dynamical tides. It's just that in this equation, most of the factors are hidden in this Q prime factor here, which is an indicator of how efficiently these tides can be excited and dissipated. And if we compare the Q primes coming from the two equations, once again, we can see that in general, the lower the value of Q prime, the more efficient is the dissipation. Okay. So sorry for the people online. So in this plot, as you can see, there is on the y-axis, the orbital distance from the stellar center, and on the x-axis, the age of the system. The cyan and magenta region represent the evolution of the extent of the stellar radiative and convective region as a function of time. This black dashed line represents the evolution of the corrotation radius, which indicates the distance above which the planets are pushed outwards and below which the planets are pushed inwards by tides. And the solid lines are orbits of planets starting at different value of the initial orbital distance. In particular, oh, okay. Is it okay now? Okay, thank you. And sorry, so the solid lines here indicate different evolution of the planetary orbit for different value of the initial orbital distance. And as you can see, indeed, if we start above this radius, the planet push outward, otherwise it pushed very quickly inward, till when it reaches this red dotted line, above which dynamical tides are at work. And here at the minimum, the following evolution is driven by equilibrium tides till the engulfment of the planet. Now, moving on to the second interaction, which is the radiative one. Also in this case, the evolutionary stage of the star plays an important role. For example, the volumetric luminosity of the star is very important to determine, once again, the structure of the planetary atmosphere. And one of the variables that is very broadly used in the exoplanetology community is the equilibrium temperature, which is given by this equation here, where you can see that the volumetric luminosity of the star is an explicit variable. But also the X-ray and extreme ultraviolet luminosity of the host stars are very important whenever the upper atmosphere layers get heated up by this high energy radiation, concurring in the process of the atmospheric mass loss. Usually for planets, this equation here, which is the mass loss rate computed in the hydrodynamic escape regime in the energy limited approximation, is used. And as you can see here, we have the XUV flux from the star as input. Now, for the bolometric luminosity, it's very easy to retrieve it from the Stefan-Boltzmann equation. For the XUV luminosity in stellar models, we need, in order to compute it, we need to account for the age activity rotation relationship, according to which we know that low mass stars' rotational properties and magnetic properties are strongly interconnected through a feedback dynamo loop. This feedback dynamo loop is itself regulated by the competing effects of differential rotation, turbulent convection, and angular momentum loss from the surface of the star. As low mass stars evolves on the main sequence, they slow down, so their rotational period increases. Then their dynamo becomes less efficient and their magnetic properties weaken as a function of time. And this is observed here in this plot from Bouvier et al. 2014, where you have the surface rotation rate or the rotational period on the y-axis as a function of the stellar age. Here I highlighted the main sequence, and you can see that because of the angular momentum lost through magnetic winds, the stars spin down in a monotonic way. At the same time, their magnetic properties weaken, as just said, and this is observed if we look at their X-ray emission. You can see this in this plot where we have the ratio of the X-ray luminosity over the bolometric one on the y-axis as function of the stellar rotation period that we can consider as a proxy for the age, with all the caveats that come with that. And usually this distribution is used to calibrate the relation between the X-ray luminosity and the rotational period in models. We can do a little bit better than that if at the place of the rotational period, we put the stellar Rossby number, which is the ratio between the rotational period and the convective turnover time, which is defined as the time scale needed for a convective bubble to travel from the base of the convective zone to the dissolution point. This last distribution is generally used to do some fittings and obtain some broken power laws which relate Rx with the Rossby number. From this relation, we can derive the X-ray luminosity. From the X-ray luminosity, then it's possible to derive the extreme UV1. And finally, we put everything in this equation, from which we compute the mass loss rate and integrating it backwards in time, the lifetime mass loss from planetary atmospheres that you can see here computed for a planet having a mass of 1.05 Earth masses, orbiting around a 1.4 solar mass star. Given all these very strong connections between star-planet interaction and the host star evolutionary stage, of course, we need to have a very accurate knowledge of the host star. And in this context, I'm sorry that you cannot see it. I don't touch it, sorry. There key synergies were established between the star-planet interaction, exoplanetology, and asteroseismology community. In particular, asteroseismology has provided in the past few decades an incredible and increasing amount of data for solar-like oscillators. And there has been a true revolution starting from the launch of CoRoT in 2006. We went from having a bunch of stars, less than about 20 solar-like oscillators before CoRoT, and now we are at around more than 10 to the 5 solar-like oscillator, and there will be more in the future with WCURS now renamed Roman Space Telescope. Asteroseismology is very important also for exoplanet detection because most of the methods rely on planet-to-star properties. This is the case for transit, where the transit depth depends on the ratio between the planetary radius and the stellar radius, but also for radial velocity, where the semi-amplitude depends on the ratio between the planetary mass and the mass of the star. And in this respect, asteroseismology is a very powerful tool, providing data with unprecedented accuracy and precision for the stellar age, radius, and mass. In this plot, some average fractional uncertainty are given from Silva et al. 2015 for Kepler stars. But for some subsamples of stars, these limits can be pushed even below these percentages, down to 4.1% for the stellar age, which is impressive. Thanks to this very accurate and precise data, we can better constrain the stellar model, having much better knowledge of the chemical composition, the depth of the convective zone, but also transport processes and profile of internal rotations, as it is shown here in this plot from Dimao et al. 2018. Now, the aim of my work is the one of studying star-planet interaction by using as much as possible detailed star-planet interaction modeling. And in order to do that, I use the following method and tools divided in 3 steps. We start from deriving the best fit stellar model by doing an optimal stellar parameters research, which is based on global and local minimization techniques with different tools depending on whether asteroseismic data is available or not for the star. After that, we compute the stellar tracks from our best fit stellar model. And finally, the stellar tracks are coupled with a star-planet interaction code, in which we can compute simultaneously the tidal and radiative interaction. And from this code, we can get the tracks for the rotational period, Rossby number, X-ray luminosity for the star, and the orbital distance, total mass, and total radius for the planet, among other variables. This method has been already applied on some star-planet systems. This was the case for Kepler 444, for TOI 849, but also for stars on the red giant branch, and again stars on the main sequence, Kepler 93, and the star on the red giant branch, Kepler 91. But today I would like to present some more recent results that we obtained together with Maria Pia on GJ 504, which is an object of high interest because it's an explicit candidate for a star that underwent strong star-planet interaction. In particular, for this star, we wanted to understand whether the fast rotational period and bright X-ray luminosity could be ascribed to the inward planetary migration of a companion and its eventual engulfment. So GJ504 is a G05 solar-like star, which is also the host to a substellar companion at an orbital distance of about 43 astronomical units. This substellar companion has been discovered through direct imaging, which makes this system one of the very few discovered with such method, only the 1.4% of the total confirmed objects. And within this small percentage, only the 5% of system have a G-type host stars. The peculiarity about this star is that its evolutionary state is highly uncertain, and this uncertainty makes it very difficult to constrain the properties of this substellar companion. And that's why we wanted to study this system. Now, the uncertainty on the evolutionary stage stems from different indicators used to derive the age. On the one hand, for example, Pezzotti et al. In 2013, in the discovery paper of this substellar object, tried different methods, but they believed that the age derived from gyrochronology and chromospheric activity could be the most likely one. And they found a value of about 160 mega-year for this object. From this age, they derived the mass of the companion of about 4 Jupiter masses. But later on, Forman and Cini in 2015 carried out a high-resolution spectroscopic analysis, which led to a major revision of log G. And they found, through the isochrones method, a much larger value for the age of about 4.5 giga-years. And from this one, the mass of the companion resulted to be much larger, of about 25 Jupiter masses. This new estimation of the age is, however, at odds with what is suggested from the rotational period and the magnetic properties of the star. And thus, these authors, for the first time, invoked the engulfment of the planetary companion by the star that would have spun up the stellar surface and rejuvenated its dynamo. Dorazzi et al. In 2017 also find similar result for the age of a few gigayears, and they computed the engulfment of the companion by using a simple tidal model with fixed dissipation efficiency. More recently, Di Mauro et al. 2022 tried to employ asteroseismic techniques on test data to determine the evolutionary stage of the star, but unfortunately, they could not detect solar-like oscillation, probably because of the high magnetic activity of these stars. From the test light curves, they could still retrieve a rotational period, and this is not visible here. From Mount Wilson observatory data, they could find a magnetic cycle of about 12 years. So the question that we wanted to ask to ourselves is whether the engulfment of a close-by companion could actually be responsible for the short rotational period and X-ray luminosity observed for the star. And we wanted to study that, thank you, by using a more detailed star-planet interaction modeling. And in order to do that, we decided to study the past evolution of this star by envisioning two scenarios, one about the star without a close-by companion. So we know that there is one far away, but this is not important for strong star-planet interaction. And a second scenario in which we imagine that massive planets formed or migrated very closely to its host star. In order to do this study, we used the same method described before, but as fourth step, we could compare our our theoretical tracks with observational value, in particular for the rotational period of about 3.4 days and for the X-ray luminosity, from which we consider both archival data from PROSAT and also new X-ray data from eROSITA. Now, just a few words on the first two steps. For our global and local minimization techniques, we consider this spectroscopic data as inputs. And for the radius of the star, we took the interferometric radius from Bonfoy et al. 2018. And from the global and local minimization technique, we found an age of about 2.11 plus minus 1.75 gigayears, so quite a large uncertainty. While for the mass, we found 1.29 solar masses, just to give you an idea of what kind of host star we have. For the X-ray data, thanks to the collaboration with Hans Magada from the University of Tübingen, we looked into the different observations that were performed between 2019 and 2022. This star has been observed 5 times. As you can see, there are not huge variation on the X-ray luminosity, but it's very interesting to have different scans at different years because this gives us a sense of how much these stars can vary during part of its magnetic cycle. Now, moving towards the result, let's start from the first scenario. As I told you, we want to compare our theoretical tracks with observational data. So we wanted to study the evolution of the surface rotation rate and compare it with the observed one. So for low mass stars, we know that it's very difficult to know which was the initial value of the surface rotation rate, because by the time they reach the main sequence, all the tracks overlap because of magnetic braking, so there is a strong degeneracy. For this reason, at the beginning of the simulation, we had to account for a very large range of initial surface rotation rates, from 1 to 18 times the value of the sun. And the result that we obtained is showed here in this plot, where we have the surface rotation rate as a function of the age of the star. Each track corresponds to a different value of omega in. And as you can see, the tracks start at different time because we account for different protoplanetary disk locking timescale. This red dashed line here represents the critical velocity. But what we need to focus on is the comparison between the tracks and these dots, which represent the observational data with a significant error bar. As you can see, in terms of overlaps, the tracks overlap with the data only if omega in is larger than 10 times the value of the sun, and only for the youngest value of the age which is allowed from our model. At least this is what we obtain with the regular magnetic braking modeling. But we know that Loma stars, it has been theorized by Jennifer Van Saders in 2016 that these stars might undergo a weakened magnetic braking regime whenever their Rossby number, whose tracks are shown here, crosses a certain critical threshold, which is taken in this case from Metcalfe 2024. And we see that this star would cross this threshold when its surface rotation rate is already pretty smaller compared to the observational data. So this phenomenon doesn't seem to be responsible for the high rotation observed for this star. Finally, we retrieve the X-ray luminosity tracks that we compare with ROSAT and the Rosita data. In this case, we did not find any overlap between the tracks and the data. So for this scenario, there is not a global reproduction of the observational data, and probably is not the most favorable one to describe the evolution of the star. Moving on to the second scenario, in this case, we repeated the same simulation, but put a 3 Jupiter mass planet at a 0.025 orbital distance around the star. And of course, in this case, because of tides, the orbit of the planet, which is indicated by this solid blue line, is immediately impacted by tides. And you see that the planet moves inwards here, driven by dynamical tides, and then it moves inwards again because of equilibrium tides, till when it reaches the rush limit. At this point, the planet, we assume that it gets very quickly destroyed and transfer the majority of its angular momentum to the stellar surface. Because of this transfer, the stellar surface gets accelerated, and you see that this acceleration is indicated by this spike on the tracks. It's interesting to see that the higher the value of the initial surface rotation rate and the earlier the engulfment of the planet occurs. So if we consider the highest value in our range, the engulfment occurs during the Freeman sequence. So there is no signature on the following evolution. So we can exclude this value as possible rotational history for this star. If we look at the Rossby number, there is a similar behavior, but mirrored. So the dynamo process inside the star can be rejuvenated because of this engulfment. And finally, if we look at the X-ray tracks, in this case, we can find an overlap between the observational data and the theoretical and simulations. Comparing the two plots in particular, we see that the global overlap is obtained for omega in smaller than 7 times the surface rotation rate of the sun. These results were obtained just for one case, so planet with 3 Jupiter masses, with a mass of 3 Jupiter masses at a certain orbital distance. But we want to explore a bit more the parameter space, so we consider a range of value for the initial orbital distance and for the initial mass. And for the star, we consider 3 values, which typically represent the evolution as a slow, moderate, and fast rotators. And by studying these parameter spaces, we could find some region in which, according to which the tracks would reproduce both rotational period and X-ray luminosity, and these regions are represented by the black hatched line. So as you can see, these regions are pretty broad for what concerns the initial mass of the planet, much less broad for what concerns the initial orbital distance. This is the case of the slow rotator. For a moderate rotator, we found a similar result, but a different shape of this region. And finally, for the fast rotator, as found also before, there is not at all compatibility between the tracks and the observational data. So, going to the concluding remarks on this project, we try to study the fast evolution of GJ504 and try to reconcile different age estimation by invoking the engulfment of a planet. By considering these two different scenarios, we found that the star with close by companion seems to better reproduce the observational data. And as future perspectives, we submitted a proposal for espadons, and if it will get accepted, we hope to have more information about the large-scale magnetic field of the stars and its braking properties. Hopefully, there will be more monitoring from eROSITA to cover an entire magnetic cycle. But of course, a final answer on the evolutionary stage can only be provided by asteroseismology. Now, just a few words on this other project that we are working on together with Maria Pia Di Mauro. So as I showed you before, to retrieve the X-ray luminosity track for a star, we studied the distribution of stars on this plane, the Rx versus Rossby number plane. In this distribution, the major source of uncertainty is the computation of the convective turnover time, which is not an observable. So we need to assume or to use some different prescriptions. And different prescription might give very different results when we want to fit this distribution. Indeed, with these three different prescriptions from Wright et al. 2011, 2018, and from Kranman and Sarr 2011, we can have different results for what is this saturation Rossby number, which indicates the knee of this broken power law here, but also for the slopes of these power lobes in these two emission regimes. And of course, when we implement these different power laws in the simulations, we can get very different results whenever we compute the mass loss from planetary atmosphere. And we realized that when we studied Kepler 444. As mentioned before, this is one of this is a peculiar exoplanetary system where the host star is the companion to a binary system of two M dwarfs. 5 sub-Earth-sized planets orbit around the primary. What is good is that for this star, there are very good asteroseismic data, so we know with a good precision what is the mass, the radius, and the age. This is one of the oldest planetary systems containing sub-Earth-sized planets. Moreover, for the host star of this system, H1 Lyman alpha variation in absorption have been observed, which could indicate the escape of hydrogen-rich atmospheric atmosphere from the two outermost planets. And what we wanted to understand is whether after 11 gigayears, such small planets could still retain any of their hydrogen. And once again, we use the same method to understand that. And we use our star-planet interaction code. But as the referee suggested at the time, we should have experimented different fitting formulae to this distribution of stars. And in particular, we tried to use a recalibration from Wright et al. 2011 and a more recent one from Johnston et al. 2021. By using these two different prescriptions, we computed different X-ray luminosity tracks, as it is shown here on the plots. And when comparing with the observational value for Kepler 444, we see that in the first case, there is at least a sort of overlap, while in the second case, the tracks tend to overpredict the X-ray luminosity by about 1 order of magnitude. And when we compute the lifetime mass loss, in the first case, some atmosphere can survive by the end of the evolution, while in the second case, everything is removed. I forgot to mention that this is the position of Kepler 444. So as you can see, it seems to be in a sort of evolutionary sequence with the sun. So what we want to understand is whether and why for Kepler 444 we have such a big difference between the two prescriptions, and if we can constrain these broken power laws and adapt it to stars belonging to different spectral types. And again, in order to do that, we need to have very well constrained stars. For this, we look in the best sample of stars that we have so far, which is the Kepler Legacy. It's a sample of 66 stars, which have been observed for more than 1 year, with individual oscillation frequencies, and for which the average uncertainties on the radius, mass, and age are shown in here. For these stars, we retrieve the rotational periods that we need for this relationship from Santos et al. 2021 and from Oliver Hall et al. 2021. And by this cross-match, we obtain finally 50-point targets. These are very broadly the properties of the star. So we have masses from 0.75 up to 1.6 and ages between about 1.5 and 11 gigayears. Of course, the relation between the two rotational periods shown here is not a one-to-one, because in the case of Santos, it's a photometrically derived rotational period, while for Oliver Hall, it is derived from asteroseismic studies. And we also had to look for X-ray data. So we found a cross-match, by doing a cross-match result, we found three correspondences, maybe three matches, sorry. With XM and Newton, again, three matches. But for the majority of stars, we had to ask to people working within the Rosetta consortia, either in Germany or in Russia. And most of the Kepler stars happened to be in the half of the sky of the Rosetta Russia. We obtained X-ray data for 13 stars and upper limits for the remaining 31 stars. And this is very interesting because I think that it's definitely dead. Oops. Oh, okay. These are very preliminary results. We are really working on that right now. We started to plot these stars with different prescription of the convective turnover time on this plane. We see that when we use Kramer and SAR 2011, there is a shift of this star, an horizontal shift compared to the bulk of the distribution, which is due to a very different derivation of the effective temperature, but this is expected. I can explain later on if we have time. We also started to look how these stars behave in the X-ray versus age plane. And here I compare with theoretical tracks for one solar mass stars. Here the colored stars represent X-ray data from open cluster for which we know a little bit better the age. And these oranges points are Kepler legacy stars. This red vertical line is the sun. This is not an error bar, but it's the actual variation of the sun in the X-ray emission across an entire magnetic cycle. There is still a lot to do. We need to add the upper limit. We need to add other stars which have been already characterized asteroseismically from Metcalfe between 2021 and 2024. And reaching the summary on this project. So the goal is to recalibrate these Rx Rossby number and LX age relationships. We hope to get a calibration based on spectral type. This might be very important to interpret some exoplanetary population features, such as the Regis Valley or the Oort-Neptune Desert. There is still a lot to do, and one of the challenges is to see if there is any hint of weakened magnetic braking in terms of X-ray emission. And at least to our knowledge, this is the first study looking at the X-ray properties of the Kepler legacy stars. This is my definitive conclusion. So star-planet interaction are crucial to interpret the formation and evolution of exoplanetary systems. In order to do that, it's important to account for the hot star and the planetary evolution at the same time, and all the inputs from asteroseismology are of key importance. This kind of interaction can be better constrained in exoplanetary systems for which we have good asteroseismic data. Having a better understanding of the activity-age rotation relationship, it's also very important to understand in general the evolution of Solar-like and Luma stars. Star-planet interaction can also be very useful to derived stellar properties that cannot be otherwise obtained. This is the case for the breaking down of the rotational history degeneracy. And to conclude, asteroseismology plus stellar activity and star-planet interaction are very important to constrain planetary habitable zone. And this is one of the key goals of the Plato mission that will be launched probably in 2026. I would like also to acknowledge the contribution of all the collaborators listed here. And thank you very much for your patience and for your attention.
Questions?
Let me ask a question. I don't agree. Is there any evidence from asteroseismology of magnetic field, some electromagnetic in other stars? If there are.
So to my knowledge, I haven't heard about this particular evidence from asteroseismology, but maybe Maria Pia is the best person to ask to this kind of question.
No. This will require a longer, longer observation, that's for sure. There is some possibility to get out the Rossby number, for example, but the actual one. I mean, as long as you can retrieve some data, it's just for 30 days observation for a single star with Kepler. So that will require other kind of observation. So, in field two, so
Okay.
but as far as I understood, you just what you need from X-rays is the level of luminosity or flux of these sources. You are not interested on the shape, spectral shape, or variability or something.
So we discussed about that with Enza, who did the study for DJ504. Maybe I don't have the spectra here, but if you want, I can show you from the paper. So she also analyzed the actual spectrum for the star in order to see. I'm not familiar with X-ray observation as well, so I try to be as clear as possible. She wanted to see if there was, for example, any flaring from the star. And especially whenever we want to get this X-ray luminosity, she tries to derive it from the quenching state of the star. So she wants to exclude this flaring activity that otherwise would somehow pollute the data that we want to compare with our theoretical tracks. So she looked at this at the spectra, but at the end for the comparison, we just compare the value of the X-ray luminosity.
In such a case, if you don't need a very high signal to noise spectrum, if you want to follow with XMM Newton, for example, some of those targets, you can ask for this in which they times to time an observation of one or two targets in the full EO of the satellite, and it could be helpful to feel the one target you have. If you want to have more information, X-ray. Of course, you can. It's not guaranteed that your observation will be done, but if there's left space between an observation and another, they just make the target easy to follow, and you will get a flux or a very low signal to noise spectrum. But if the spectrum is not your main point, we use maybe.
Actually, we thought about that before the deadline for XMM Newton. But at that time, we were still waiting from a reply from the eROSITA Russian consortium. So we didn't know for how many stars we could already get some X-ray data, which is, I think, one of the requirements whenever you want to submit a proposal for XMM Newton, to see if these stars are already on.
It's particularly relevant in the full field because they have to know where the targets are located, because they are putting target when there's a hole between an observation and another. So the coordinates are also, you have to know. With respect to eROSITA, of course, with XMM, you also have a higher energy band. So you are not focusing the soft. Although I think that in your case, the soft is
the main one.
But in XMM, you have a larger energy band. It's just an option.
No, yes, actually, we want to do that. And since we missed the deadline for XMM, we would like to apply for Chandra in the next spring to see, probably to select the most interesting targets from this sample. But thank you for a nice suggestion.
There is a question from colleague. Is in the engulfment scenario, do you expect that the compact will survive very close to the star, complete loss of the engulfment planet?
So from some works which focus on simulations following the destruction of planets at the Roche limit, it seems that the time scale for the complete destruction of this object is very small. It's about 10 to the 2 to 10 to the 3 years. And in this simulation, it seems that there is no any compact object left But I guess that it also depends on the internal structure of the planet that you are considering. The other point is that radial velocity measurements and observation have been done for GJ504. And according to this radial velocity measurement, it seems that they can exclude the presence of any planet with a mass above, if I'm not mistaken, 60 Earth masses is around. So from this kind of observation, they exclude objects with this mass. But of course, if there is any object with smaller mass, this is unclear.